So I'm going to go through and explain the summer review worksheet. So you guys really should have treated this like a test. And so go through and grade yourself, and any concepts, especially the concepts that you were uncertain of or that caused you pause, make sure to go back and review practice problems with that. If anything was super easy, that is stuff that you don't need to go over again. But the challenging material, that's what you really need to be focusing on. So for 1A, it says, below draw a complete Lewis electron dot diagram for SCl4. So SCl4, when you count the total number of valence electrons, it has 34. And so this is the structure that I drew. Because its electron domain geometry is trigonal bipyramidal, it has 4 bonding and 1 non-bonding domain, the shape is going to be, or the molecular geometry is going to be seesaw. And then when it asked if this molecule is polar or nonpolar, I noted that it is going to be polar, and the reason why is because the dipoles do not cancel, because if chlorine is hogging electrons towards it, there's going to be nothing counteracting that pull downwards with a pull upwards because there's a lone pair of electrons here. So the dipoles do not cancel. In D, it says, what is the strongest intermolecular force that SCl4 experiences? Well, because it is polar, it can experience dipole-dipole forces. However, since it does not have hydrogen and fluorine, oxygen, and nitrogen, it cannot experience hydrogen bonding. So SCl4 has dipole-dipole forces and it has London dispersion forces, but the strongest type is dipole-dipole forces. For NO2-, because it has 18 valence electrons, this is going to be the Lewis structure for that. Keep in mind, this is a case of resonance, so you've got to draw both versions in order for us to properly represent the fact that these bonds are actually going to exist as an average of a double and a single bond. Okay. For F, without using any outside sources or even looking at your periodic table, which molecule, SCl4 or NO2-, would have the shorter bond length? So what it's wanting you to note is if you look, SCl4 has only single bonds, while NO2-, if I were to average these two bond lengths, so 2 plus 1, and divide that by 2 to get the bond order, that would be in bond order of 1.5. So since NO2- has a bond order of 1.5, while SCl4 only has a bond order of 1, that means that NO2- is going to have a shorter bond length. Okay, because the higher the bond order, the shorter the bond length. For G, it says, why can sulfur form an expanded octet but nitrogen cannot? So keep in mind, in order to form an expanded octet, an atom needs access to the D sublevel. And so since sulfur is in the 3rd energy level, it can form an expanded octet, but since nitrogen is only in the 2nd energy level, it does not have access to the D sublevel, and therefore it cannot have an expanded octet. In 2A, it asks, why is Br2 a liquid at room temperature while Cl2 is a gas? Well, both of these, I need to reference both of their intermolecular forces, and they both have London dispersion forces. So when I compare them then, I need to compare the number of electrons. So since bromine has more electrons than chlorine does, it's going to be more polarizable, enabling it to have a stronger London dispersion force. And therefore, since its London dispersion force is stronger, that's going to cause it to be a liquid at room temperature, while chlorine, which is weaker, is a gas. It gets even more severe if you look at your halogens, by the way. Iodine, I2, is actually a solid. So it has so many electrons that its intermolecular force is so strong that it's actually a solid at room temperature. For B, it wants to know which has a higher boiling point, CH2O or H2O. So CH2O, if you draw that out properly, you'll see that that molecule is polar. We actually saw that a couple of times in the summer worksheet, so that's why I didn't include the drawing here. And it experiences both dipole-dipole forces and London dispersion forces, while water experiences hydrogen bonding, dipole-dipole forces, and London dispersion forces. If you didn't include dipole-dipole forces, that's totally fine. It's kind of implied since hydrogen bonding is a type of dipole-dipole force. Now, since water has a stronger intermolecular force, since hydrogen bonding is stronger than dipole-dipole forces, that means it will have a higher boiling point. All right, so for 3, I give you the mass of the sample, and I give you the volume of the gas, and the pressure, and the temperature. So I used PivNert, and I solved for my number of moles. Once you know your number of moles, since it's asking you to determine your molar mass, you can simply take your mass, divide by your number of moles, and you'll get your molar mass. Do keep in mind that since 30 has 1 sig fig, I had to way overround my molar mass, which makes me a little uncomfortable, but I was keeping consistent with sig figs. Okay, so that was 3. For 4a, rubidium has 2 isotopes, 86 and 84. What do they have in common and how are they different? Well, isotopes of an element are going to have the same number of protons, because remember, as soon as you change the number of protons, you've changed the element that you're dealing with, and they have the same number of electrons. And therefore, because they have the same number of electrons and protons, they're going to react similarly. The one thing that they do differ in is their number of neutrons, and therefore their mass numbers will be different. For B, it asks us to determine the percent abundance of rubidium-86 if the average atomic mass of rubidium is 85.468. So I have my 2 isotopes. Remember, their percent abundances have to add up to 100%. So if I have rubidium-86, so it's going to be 86 times X, because that is 1% abundance that I don't know, plus rubidium-84 times its percent abundance. And the way that I determine that is say, okay, well, the percent abundances have to add up to 100%. So X, if one of them is X, the other one is 1 minus X. All right, so that's the percent abundance of the other one, and that equals 85.468. When I do out my math, I get 73.4%, and I just rounded to 3 sig figs. You can round however you want, honestly. Okay, so that's B. For C, it asks for the mass spectrum. So I drew this. I showed the relative abundance on my y-axis. I've got my 2 isotopes here, and since the relative abundance of rubidium-84 is about 26.6%. I showed it right over 25%, and then this one was 73.4%. So that's my mass spectrum for the isotopes. For 5, it has us getting into equilibrium, so it wants me to write the expression. Do remember, notice I left out iron oxide here and iron, and that's because in order to include a substance in your equilibrium expression, it can only be an aqueous solution or a gas. If it's a liquid or a solid, it is excluded from your equilibrium expression. It does not contribute to the equilibrium constant. Okay? For B, it simply wanted me to plug in values and solve, so I got 91, rounding to 2 sig figs. Okay? For C, it wants to know what's being favored. Well, the products are favored since my KEQ is larger than 1. And then finally for D, it says identify what's being oxidized and what's being reduced. So here I've got this lovely reaction here. And I actually don't know why I didn't create a brand new problem for that, but it's D. So here I've got my reaction. Oxygen has an oxidation number of -2, except when it's a peroxide, when it's -1, or when it's with fluorine, because fluorine is always -1, in which case oxygen is +2. But here, it's just how it typically is, so -2, so nitrogen would have to be +1, and then these 2 elements are by themselves, so they're both 0. So nitrogen goes from +1 to 0, which means it's gaining electrons, so it is being reduced, while oxygen loses electrons, so it is being oxidized. All right, for 6, given that reaction, what is the concentration of N2O? So I wrote out, this was from this problem right here. So this definitely should have been the beginning of 6. I apologize. This is 6, and then this would be 6b. But I'm going to use this reaction here. So I've got N2 squared times oxygen all over concentration of N2O squared. I plug in my values. Do make sure you should be cross-multiplying, so 7.3 times 10 to the 34th times my concentration of NO2 squared. And then you can divide both sides by your 7.3 times 10 to the 34th. I showed what I got for the concentration of N2O squared. I then now need to square root that, and I get the concentration of N2O is 7.4 times 10 to the -30th. Okay. For 7 here, I've got to manipulate these 3 reactions in order to get this overall reaction right here. So I look for major players. So B2H6 I see is right here, so I'm going to leave that there. All right. Another major player, I need 6 Cl2s. So notice the only place I have Cl2 is from this guy right here. And so I need to multiply this one by 12. Other major players would include BCl3. So notice I need 2 BCl3s. The only reaction that provides that is the top one, but it's on the reactant side right now. So I need to flip this one and then multiply by 2. Okay, and so when I do all of that and add those reactions together, you can see all my work here, I end up getting this overall reaction. So I'm going to take 1.4 times 10 to the -5th, raise it to the -2nd, then multiply by 0.0230, and then multiply by 2.1 times 10 to the 2nd, but I'm going to raise that to the 12th. And what I end up getting is 8.6 times 10 to the 35th. All right, number 8 has you working with Le Chatelier's principle. So it shows you this reaction here, and it asks you to explain why the solution turns from clear to pink when you add water. Well, since water is a reactant, since you're adding a reactant, the system is going to shift to the right. For B, you're adding silver nitrate. Remember, if you're adding silver nitrate, it might seem completely out of the blue and that it wouldn't affect your equilibrium. But it does, and the reason why it does is by adding AgNO3, you're adding Ag+. And so Ag+ will form a precipitate with OH-. It's going to form AgOH, so it's going to form a solid, which is going to remove hydroxide from the solution. It's going to decrease the concentration of hydroxide. And since the concentration of hydroxide is decreasing, that's going to cause a shift to the right. For C, it says when I increase the temperature of the pink solution, it turns clear. So why would it shift left when I increase the temperature? Well, that lets me know, hey, your reaction here is actually exothermic. So if heat is on the product side and I raise the temperature, that would explain why I have a shift to the left. All right, for number 9, water is the base because it then becomes H3O+, so it is accepting hydrogen ions. It's the bad rule. Bases accept, acids donate. H2PO4 here is an acid because it donates a hydrogen ion to become HPO4 2-. For number 10, wanting you to review making solutions. So I want a 0.150 molar solution and I want 50 mils of that. So I'm going to use my molarity formula here because I'm dealing with solid sodium hydroxide. I'm not dealing with a dilution. I'm going to multiply here. Do keep in mind the 50 mils needs to be in liters, so that's why I moved my decimal place 3 places to the left. I get my number of moles, and then what I need to do is I need to multiply by the molar mass of sodium hydroxide, which is 39.997. And so when I multiply 0.075 by 39.997, I get 0.3 when I round to just 1 sig fig. Okay? And so in my explanation for how to make this solution, remember, go back to and look at the tools that I provide you with. But what you need to do is you need to measure out 0.3 grams on an electric scale because it's a solid. And then I'm going to add it to a 50 ml volumetric flask because that's my most accurate tool for measuring exactly 50 mils. And then you'll add enough water to get a final volume of 50 mils. Okay. For number 11, this is a lab that we will do this year, but you guys already did practice problems with collecting a gas over water. So let's look at this. The first question, so it gives me all of this data. It first asks me how many moles of butane did I collect? Well, since this is a gas and I know the pressure that is being experienced within that graduated cylinder, and I know that pressure by simply taking the total atmospheric pressure and subtracting from that the water vapor pressure, that will be the pressure of just my gas in the graduated cylinder. When I convert that into atmospheres, I get 0.97 atmospheres, so I plug that in there. Do keep in mind that it is a longer value, and I kept that value in my calculator. So I didn't actually round to 0.97. Then you're going to multiply by the volume that the gas displaced of water. So that was 164 mils. So I converted that to liters. I'm solving for my number of moles. There's my R value, and then my temperature was 21 degrees Celsius, so I converted that into Kelvin. So my number of moles is 0.00659. Then it asks for the molar mass of butane. Well, I first need to determine what mass of butane I added to the container to begin with. So I started with a mass of 21.77 grams. Then I added enough butane so that at the end its mass was 21.44. So when I subtract, that gives me the mass of butane I added, so 0.33 grams, divided by my number of moles, and I get a molar mass of 50.1 grams per mole. Okay. For number 12, it says red light has a wavelength of 680 nanometers. How much energy does a photon of red light have in kilojoules per mole? So the first thing I need to do is I need to get out of nanometers into meters. Then I'm going to use my speed of light formula in order to determine the frequency. And so I plugged in my wavelength and my speed of light, and the frequency that I got was 4.4 times 10 to the 14th. Now, I didn't round this in my calculator. I kept it in there. Then I'm going to plug that into my energy formula to determine my energy. So here's Planck's constant. Here's my frequency formula. And so I got 2.9 times 10 to the negative 19th. So the most important thing for you to note when you're using your energy formula and using frequency and wavelength, the units for energy that you get are going to be in joules per photon. But this question, because it's per photon, because we're measuring the wavelength of each photon. Now, the important thing for you to note is that's not what's being asked. You're being asked what the energy is in kilojoules per mole. So the first thing that I did here was I got out of joules into kilojoules. So now I'm in kilojoules per photon. And then I got out of photons into moles, and there's an Avogadro's amount of photons in a mole. And so when I did that out, I rounded to 2 sig figs, and I got 180 kilojoules per mole when I rounded to 2 sig figs. Okay, the PES for sodium is going to be 1s2, 2s2, 2p6, 3s1. Lovely there. Do make sure to go back and remember if I said, for example, hey, also draw, on top of this, draw the PES for magnesium. Make sure that you would be comfortable doing that, right? So magnesium is just going to be to the left of this, right? Because as you move across your PES, the binding energy decreases. And so since magnesium has more protons than sodium does, all of its peaks are going to be to the left. And then also it's going to be a 3s2 peak instead of a 3s1 peak because it has 2 valence electrons. Finally, for 14A, Cobalt 3+, the most common mistake that students make, they say, okay, I've got 3p6, 4s2, 3d7 for Cobalt, and they take 3 electrons away from 3d. Remember, when you're taking electrons away from an element, you need to remove them first from the highest energy level. So 4s is the highest energy level, so you're going to remove it from 4s first. So I got rid of my 2 electrons from 4s, and then I removed 1 additional electron from the 3d sublevel. Okay, and then I drew my orbital diagram here for you to see.